we're going to be doing practice with finding lines and planes, which is going to be a great way for us to use our tools, namely our dot product, which is great for testing if things are orthogonal, our cross product, which is great for making something which is orthogonal, and of course the most important thing, geometric intuition, which is very foundational because geometry is where calculus is built on. So we need to make sure we have that solid geometric intuition going forward. And we get that through practice. So I think that we might have a bit of practice in this topic. And the more you do, of course, the better your intuition gets and the better you're going to be positioned to succeed later on. So it's important that you do as much practice as you can. If you're following along with the video, make frequent use of the pause button. See a problem? Pause and start working on it. And start thinking, okay, how do I approach this problem? What's the picture? As a word of excitement, I don't want to say a word of warning, we're getting to the point where oftentimes there are multiple ways to solve a problem. Sometimes we'll solve things in multiple ways, sometimes we won't. Just because you solve it differently than I solve it doesn't mean that either of us is wrong. We can both be right. Of course, the answer should agree. So, well, let's get going and let's see what happens. Our first problem. Warm up. Find the normal vector for the plane 2x plus 5z equals 3 plus 4y. This is a nice warm up. It says, look, we have a plane, and a plane, remember, you say, look, it's something on the form ax plus by plus cz equals d. And so we say, well, we look for the coefficients of a, b, c. Now, here's where we have to be careful. We say, oh, do we just read off the coefficients for a, b, c? Well, it'd be what's in front of the x is 2, what's in front of the y is 4, and what's in front of the z is 5. So 2, 4, 5? Careful. And the answer, of course, is we can't read off the coefficients until we sort of put things into the right format. So in this case, move the 4y across. 2x minus 4y plus 5z equals 3. Now, that you put it into this format, now we read it off. So our normal vector would be 2, negative 4, and 5. And we're done. All right, so this is, don't worry, I promise, we'll have some more challenging ones as we go on. But this is just to remind ourselves, okay, we want to make sure we're comfortable with this idea of moving between plane and normal vector. And so if you're going to start with the plane and grab the normal vector, pay attention. If the variables are on different sides, put everything to one side, then read off your coefficients. Life is good. All right, well, on to another problem. Find the line through the points 5, negative 2, 3, and 7, 4, 1. So we have 2 points. Now, whenever we think of a line, we say to ourselves, what do we need? Well, we always say we need 2 things. We need a point, and we need a direction. And that's it. If we're finding a line, we must have those 2 things. And if we have those 2 things, we found the line. Now notice, we don't lack for points. We have 2 points, twice as many as we need. So which one is the right one to use? Exactly. It's not that there's a right one and a wrong one. It's just we have 2 points. Regardless of which one you pick, it'll be the same line. The final answer might look different, but the line is the same. So we'll pick one. Let's suppose 7, 4, 1. All right. So there we go. There's our point. 7, 4, 1. What about direction? Well, we need to go and find a vector that's on the line. And if we think about what we have, well, we have a line and we have 2 points. So there's a drawing of our current situation. We say, okay, perfect. What we can do is we can find a vector that's on the line. We just simply connect. And so we can say that will be our vector. So we ask ourselves, all right, what's the change? 5 went to 7. Well, that is 2. Negative 2 went to 4. All right, that's 6. 3 went to 1. Negative 2. So a vector, and I'm emphasizing the word a vector, which is on this line, is 2, 6, negative 2. Now, do we have to use this vector? Well, we have to use a vector. So what can we do? Well, we can use this one as is, no problem. And so that's fine. Well, the other thing we can do is say, hey, why don't we ask ourselves if there's a nicer vector? And by nicer, we can always scale. So you can scale as needed. Notice that all these numbers are even. So what we can do is scale by a factor of a half. Or if you like, divide each entry by 2. So if we did that, which is perfectly allowed, we can have 1, 3, negative 1. Now, does it matter which direction we use? No, because it'll still be the same line. What we should think of is that our parametric form, our vector form, whichever format we use, is really saying, here's a set of points, a collection of points. And collectively, these points make the line. What's happening is that our description will be slightly different, but ultimately the set of points is the same. We could have also, by the way, gone in the other direction. Again, that's just a factor of scaling. In that case, a negative 1. Scaling by a negative 1 just means reversing direction. So now we have our important pieces. We put them together, we'll get our line. So the way I like to do it, I always prefer parametric. I don't know if there's a good reason for it. I just do. I like to write it, okay, x equals y equals z equals, and I say, what's my point? 7, 4, 1. So that just doom, 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 doom. Now, what's my direction? 1, 3, minus 1. So plus 1 times t, plus 3 times t, plus negative 1 times t. See? Point, direction. And there you go. Now, of course, you can clean it up. And things like 7 plus t, y equals 4 plus 3t, and z equals 1 minus t. And we're done. Easy, easy. All right, well, good. Let's keep going. And we'll go on to our next problem. All right, find the distance from the point 2, 3, negative 4 to the line x equals minus 1 plus 4t, y equals 3 plus 2t, and z equals 5 minus 7t. Now at this point we'll just say let's just use the formula. We'll do some problems later on in another session where we say here's some other options that we have. But for now, suppose we just use our formula. So we probably need to remind ourselves of the formula. Our formula says, suppose you have a line, you have a point, we'll call it, I don't know, Q. It's on our line. And then there's a vector V, that's the direction vector. And then there's a point P. And you're after this length. Well, the length, we'll call it length. So length here stands for length. That's how it's easy to recognize what it stands for. So the length is equal to the magnitude of the vector QP cross V divided by the magnitude of V. So that was the formula we got for the distance between a point and a line. So we start saying, okay, well, do we know things? Yeah. In our case, we could say P is the point we're looking for. That's 2, 3, negative 4. Q, well, that's the point on the line. So we ask, well, do we have a point on the line? We have infinitely many points on the line. We just need one. Well, how do we pick one? Oftentimes it's easiest just to read it off. And you can think of it as like set t equals 0, or reading the point, however you like to think of it, negative 1, 3, 5. You can, of course, use other things. You could say set t equals 5, or t equals 2, or t equals 100. Our goal, though, is to keep things simple. Problems are already complicated. We don't want to make them more complicated. And more complicated usually means bigger numbers. try to keep the numbers in check. If we keep the numbers in check, things work out. How about our direction vector? Well, for that, we read off our coefficients of t. 4, 2, -7. All right, there we go. Now, what do we need? Well, we need the vector connecting our 2 points. Now, by the way, you might say, do I have to pay attention? Is it Q to P? Is it P to Q? And the answer is, in the end, it won't matter. Because the difference from Q to P versus P to Q, in terms of the vector, is a sign change. But because in the end you're taking a magnitude, the sign change will just whoosh, go away. So don't worry too much and panic like, oh no, which way does it go? It's okay. Either way works. So going from Q out to P, what do we get? Well, -1 to 2. This vector, I should make it clear it's a vector, right? Vectors have the brackets, points are the more round brackets. Okay, so Q out to P. We have -1 went to 2. So that's a change of 3. 3 went to 3. 0. Perfectly fine. It's okay to have a component entry of 0. No worries. 5 went to -4. All right. So 5 goes to -4. That goes down by 9. All right, so there's our change. Up by 3, no change, down by 9. Now you might be saying, can we scale here? Because in another problem we said, oh yeah, scale V doesn't matter. We can't scale here because it's not just the direction of QP that matters. The magnitude of QP matters. When magnitude matters, don't scale and get rid of things. You have to keep track of them. So our next step, we better figure out what this cross product is. Let's see that. What do we have? Well, we're going to have QP cross V. So I'm going to have I, J, K, 3, 0, -9, and then 4, 2, -7. So I times 0 times 7, 0I. J times -9 times 4, -36J. K times 3 times 2, 6K. 4 times 0 times K, 0K. But going in the other direction, subtract. 2 times -9 times I, -18I. But again, we're going in the wrong direction. So we subtract, so it really becomes plus 18I. And -7 times 3 times J, minus 21J, but we have to subtract it. So it's going to be a plus 21J. So we end up with 18, then minus 36 plus 21, minus 15, and 6. All right. We can also write this, by the way, as 3, because all these terms have the factor of 3 in common, 6, comma, -5, comma, 2. Now, whenever we're doing cross product, we should always check. I've made mistakes before when I haven't checked. It's always a sort of a rule of thumb, is if you don't check, that's when a mistake happened. But of course, if you do check, you did it right. So we want to do it right, so we're going to check. So the way we check is we take our answer, dot it with our original vectors, we should get 0. So let's see. We'd have 18, 0, minus 18. Good. 24, minus 10, minus 14. Great. So we took our dot product of our output with both the vectors we started with, and we got 0 in both cases, meaning we almost certainly did it right. I won't say 100% of the time you do it right, but like 99.9%, that means you did it right. So good enough that we go forward with confidence. So what do we do now? Well, we really just are a few magnitude computations away. So we continue. We say the magnitude of the vector that we just found divided by the magnitude of the vector, that's the direction vector of the line. So that's 3, the magnitude 6, -5, 2, 6, -5, 2, excuse me. And then V is magnitude 4 to negative 7. Good. So that would be 3. See, I should say technically the 3 is on the inside, but then it comes out. Absolute value of 3 is 3. If it had been a negative 3, I'd put the negative out as well. So 3 square root of 6 squared, 36, 5 squared, 21. It's actually, 25. It's actually negative 5 squared. But if you square negative 5, it's going to square in 5. And then 4. Downstairs, square root, 16. That's 4 squared, 2 squared, 4. Negative 7 squared would be the same as 7 squared, 49. And, well, what do we see? 36 plus 4 is 40, plus 25 makes 65. Okay, so we have a 3 square root 65. Divide by 16 plus 4 is 20, plus 49 makes 69. And from there, we're done. We can't really do anything. There's nothing else to simplify because 65 and 69 have no common factors. And so there's no more real cancellation we could do. Well, there's kind of a small cancellation you could do. You'll notice that 69 does have a factor of 3 in it. So what you could do is, if you really wanted to, you could say, well, look, this can be thought of as the square root of 3 times the square root of 23. Now 3, you can think of it as the square root of 3 times the square root of 3 times the square root of 65. And you could cancel off the square root of 3's. So if you really wanted to, and if you were, say, a mean instructor saying, aha, let me obfuscate the answer, well, you can also write it as the square root of 195 over square root of 23. But in the end, that's what it'll become. Good. All right, so finding distance, if you know the formula, not so bad. And of course, you can derive the formula. That only takes like 10 minutes. Hardly any time at all. But as I should say, we will have other ways to solve this problem as we work through problems in other sessions. So there are alternatives out there. All right. The next problem. Find the line which lies in both the plane x plus 2y minus 3z equals 5 and 3x minus y plus z equals 7. So what's sort of the idea here? Well, the idea is we have the following. We have some plane somewhere in space, and then there's another plane somewhere else in space. And of course I'm drawing this in sort of a not ideal situation, but there we go. There are the two planes, and they're crossing. They intersect. And the question becomes, okay, what can we say about their intersection? Now, there's a couple of ways to go about this problem. So we'll talk about them. I think we'll try to do at least 2 here. So how can we start? Well, one way we should think about is we're looking for a line. Now, how do we know we're looking for a line? Well, the key is it said, find the line. Dead giveaway, we're looking for a line when it says find the line. So when we say, well, if we want a line, we need 2 pieces of information. We need a normal vector, and we need, not a normal vector. I'm thinking of planes. We'll get to normal vectors in a second here. We need a direction, which is a vector, and we need a point on our line. Okay, so we need those 2 pieces of information. Let's start with the direction of this line. What do we know? Well, we know that the line is in the planes. In fact, it's in each plane individually. So there's sort of a combination of ideas. So let's sort of see what we can say. So we'll make an observation. So our first observation, it's kind of a simple observation. It's almost so simple, we sometimes don't even think to bother to say it, which is the direction of the line, which, in other words, the vector that represents how that line changes, is inside the plane. Now, I have to put the words inside in quotes because, of course, vectors aren't tied to locations. Vectors can move. But sort of the intuition says, look, if I have a plane somewhere, and if that plane were to contain a line, so here's a line, then any vector on that from that line, so here's the direction vector of that line, is also a vector that's in the plane. Okay, so that's sort of the idea. The direction vector of the line is a direction in the plane. Well, how is that helpful? Well, now we combine that with sort of another recall. And so we could say recall that the vectors in the plane, and of course, when we talk about in the plane, you know what we mean, are perpendicular to the normal. In fact, the normal vector is meant to be perpendicular. So what does that tell us? Well, it tells us the following two pieces of information. We just sort of tie these two ideas together. We know that the direction vector of our line is in the plane, so it's perpendicular to the normal vector. So we get the following two facts. So the direction we want, in other words, our direction vector, it's got to be perpendicular to the normal vector of our first plane, which is all right as x plus 2y minus 3z equals 5, and it's also perpendicular to the normal vector of the second plane, which is our plane 3x minus y plus z equals 7. Now, this is like the ideal situation to be in. In fact, we feel really good here because we now know two different things which the direction we want are perpendicular to. Now you might say, well, that's great. Well, we just want the direction. We don't want to keep finding things perpendicular. We just want the direction itself. But no, this is really what you want. Because if you know two different directions which are perpendicular to the direction you want, you're set. You're in great shape. Because what you can say is, hey, we're perpendicular, and our normal vectors, I'm just going to write them down for reference, to two vectors. How do you make a vector which is perpendicular to two other vectors? The answer is cross product. So if you can ever say, well, I'm looking for a vector, and hey, I have two different things I know it has to be perpendicular to, you're done. Take the cross product, and life is great. So, more cross product. You're going to see this is a very big theme. We're going to be doing so much cross product, you're going to get great at it, which is good because we want to be great at doing our basic tools. So we're going to take the cross product here. Now it doesn't matter which order we take the cross product because the only change is the sign, and that's still a normal vector. Either one is a normal vector. So I, j, k, 1, 2, negative 3, 3, negative 1, 1. So here we go. I times 2 times 1. Actually, you know what? Just for fun, let's at least once do cofactor expansion. Because I know there are some cofactor expansion fans out there. So we should do it at least once and say, this one's for you. So here's a cofactor expansion. Well, how does it work? We're going to go along the first row. So we say, okay, I. And now what's going to happen is we're just going to take I, cross out the first row, first column, and we have this little 2 by 2 matrix left. 2 minus 3 minus 1, 1. And we go to our second entry, j. Cross out the first row, middle column. So in other words, whatever j is in this case, it's always the first row, middle column, and then 1 minus 3, 3, 1. And now, k. Well, where is that? Cross that out first row, last column, 1, 2, 3, minus 1. 1, 2, 3, minus 1. Good. Good. Now, here's the trick. If you're doing cofactor expansion, it's plus, minus, plus. So don't forget the middle one goes with the minus, which is a good reason to check your cross product at the end. so that you're like, oh yeah, good, it worked. So I didn't make that mistake. Well, hopefully, right? Now 2 by 2 matrices are easy. You just diagonal add, diagonal subtract. 2 minus 3, so minus 1. Okay, J, you have 1 minus negative 9. That'll be 1 plus 9, which is 10, but it's being subtracted. Minus 10, J. K, minus 1, minus 6, that's minus 7. Okay, so minus 1, minus 10, minus 7. Let's check. Minus 1, minus 20, plus 21. 0. Good. Then minus 3, and then plus 10, and minus 7. 0. Woohoo! We did it. So, great news. We now have the direction. Now, we're not done. We're not out of the woods. By the way, if you don't like the fact that they're all negative, make them all positive. No problem. That's scaling. Got to get to the point. How do we get the point? Now, we actually have information, because it's not like we have no information about where the point is. We have 2 pieces of information. So let's think about it. So to recover our point, now we go into our point phase. So we have x plus 2y minus 3z equals 5, and 3x minus y plus z equals 7. Well, notice what do we have here? We can do a quick count. 2 equations, 3 unknowns. Now, in some sense, we have sort of like, we're short an equation. If we had one more equation, somehow we feel more comfortable, because it's like, there's the right number, the right mix of equations and unknowns. You might say this is underdetermined then. And whenever you have underdetermined, what it means is you have multiple solutions. And in essence, what's happening here, another way to think about the picture of the geometry, what's going on, is because we have more variables in equations and we end up with multiple solutions, what we're seeing is that that line is a geometric representation of the multiple solutions that arise to this pair of equations. So we just need to recover one solution. So how do we do it? Well, we say, look, we have some freedom. Because we have more variables than we have equations, let's just make a choice. We have one free choice. Because, 3 variables, 2 equations, that's 1 left over. So let's make a choice. And what choice do we make? We can make our choice be any choice we want. But let's do a choice that makes things easy. And so let's simply choose x equals 0. Now, that's not the only choice you could have made. You could have said, well, let's choose x equals 5. Let's choose z equals 2. We just have to make one choice. And a good rule of thumb is make an easy choice. And so we say, okay, if we're choosing x equals 0, now what happens? Lo and behold, our 2 equations become simpler. 2y minus 3z equals 5, and minus y plus z equals 7. Now, that's 2 equations, 2 unknowns, perfect. And we're going to come up with an answer, but let's point out that our point will be 0, comma, something, something. So we have to figure out what these pieces are. Now we look for ways to combine these to get cancellation. Well, one easy way to do it is to say, let's take this second equation and multiply by a factor of 2 and combine. If we were to do that, what will happen? Well, you'll see that we get a 2y and a minus 2y cancel. That's why we did it, to get cancellation. Minus 3z plus 2z becomes minus z. 5 plus 14, 7 times 2, 14, becomes 19. So we say, all right, that tells us something about z. Z has to be negative 19. Good. Now we know our z. So that goes into there, negative 19. Well, what about y? To get y, just notice something. See, I can now plug negative 19 into here, and what do we get? Well, we can say negative y plus negative 19 is equal to 7. Well, move the y across, move the 7 across, we can conclude y would be, negative 26. I can fit. There we go. Oh, we just barely fit. Okay, so now we have a y coordinate, negative 26. And that goes there. So, lo and behold, a point which satisfies both equations would be 0, negative 26, negative 19. You can even check. So just like pick an equation, say the first equation. 0 minus 52, and then plus 57. 3 times 19 is 57. And it turns out to equal 5. All right. Well, good news is we're done, right? Because what? We can now say the following. We've got our direction, we've got our point, so we can write down our answer. X, Y, Z. So X equals 0 minus 26 minus 19. So I'm just the point, the coordinates, and then plus minus 1t minus 10t and minus 7 times t. Now, it's perfectly fine that we have a 0 showing up in our coordinate. That's perfectly, it can happen. It's okay. It's okay. No worries, no worries. Now, if you wanted to clean this up, well, okay. This is the same as saying x is negative t, y is negative 26 minus 10t, and z is negative 19 minus 7t. Okay. Good. Now, I said there's at least another way you can do this. Here's the other way you can do it. This will sound a little strange, but bear with me. Here we go. So let's suppose we started with our original equations. So I'm going to try to squeeze in the idea into this little corner. You're probably thinking, if you could fit into the little corner, you should have started with that, Steve. No. Geometry, that's what we want. We want to focus on geometry. So what we have are two equations. X plus 2y minus 3z is 5, and 3x minus y plus z is 7. So move the x's across. So if you did that, you'd get what? Well, 2y minus 3z is 5 minus x, and minus y plus z is 7 minus 3x. Now repeat the similar process that you had before, except you're going to have some x's involved. So, as an example, we do the same multiply by 2 and add. So, if we do that, so times by 2, and we add, what do we get? Well, you end up with minus z, okay, same as before, is equal to 19. That's the same as before. But now, minus x minus 6x is minus 7x. Okay, or we could say z is equal to negative 19. Oh, I'm running out of room. Okay, z equals negative 19 plus 7x. So now what have we done? Well, we've now said if we know x, we know z. If you do something similar for y, okay, what can you do there? Well, for y, what you can do is you can say, let's go to our same equation, but now, instead of multiplying by 2, multiply by positive 3. What happens? You're going to get 2y minus 3y. What's that? Well, it's minus y again. Okay, so minus y. And then here, the z's cancel. Aha! That's what we wanted. And then you're going to get 5 plus 21. Oh, 26. And then you're going to get minus x minus 9x, which is minus 10x, or multiplying y equals minus 26 plus 10x. Now you're probably thinking, ooh, these look really familiar. So what does it do? How do we get from that to a formula for the line? And the answer is, you say, but look, x can be arbitrary. So to get our final answer, we say make x arbitrary. We'll give it a name, t. Now, what is y? Well, y is negative 26 plus 10t, because x is t. What is z? Z is negative 19 plus 7 times t. And it's the same line. Now you might say, whoa, are you sure? Yeah, the minuses don't matter attached to the t, because we can just flip them all, which is the same as just saying change the signs there. So that's the way to do it, by saying, oh, look, if I have two equations, three unknowns, I just knock out a variable, or rather I should say, look, write the two of the variables in terms of the third. Third is arbitrary, and now you have the formula for your line. So that's it from an algebraic perspective. But then you miss out on all the cool beauty, the chance to do cross product. So we'd miss that if we couldn't do the cross product. That's why we did it the cross product way first. All right, well, let's try another problem. Find the point on the plane x plus 2y equals 5 plus 3z closest to the point 4, 4, negative 7. Now, notice we've done something kind of similar in spirit where we said, hey, what's the distance from a point to the plane? We're not looking for a distance. We're looking for a point. Now, how do we know we're looking for a point? Well, our clue is point. It tells us we're looking for a point. So we know our final answer should be a point. And so we start to say, well, our formula for finding the distance doesn't help us find the point directly. So probably that's not what we should do. And you're right, that's not what we should do. Let's think of the geometry, because there's a sort of a nice, beautiful geometric idea going on here. So what do we have? We think of our drawing. We have our plane here. Here it is, very plain. And now what we do is we have a point. Here it is. Now, I'm not worried about being precise. I'm worried about understanding the intuition. Intuition is the most important thing right now. So we say to ourselves, okay, we're looking for the point on the plane. Well, we don't know it. But let's suppose we did know it. Okay, if we did know it, it would be some point probably here in terms of our picture. Now, think of the picture. What's true? Well, if we were to connect these two together, it would be perpendicular. Okay, closest and nearest things are perpendicular. So, how do we use that? Well, we start going through our list of ideas, and thank goodness it's a very short list, so we don't have to go very long. We start thinking, okay, something's perpendicular to our plane. A normal vector is perpendicular to our plane. And then you're like, but wait, that's not a normal vector, that's a line segment. Anyway, line segment. We could make this a line, couldn't we? Yeah, we could. We could just keep extending it. We could say, oh, an idea. So here's our idea. We can say, let's find a line. So find a line. Now, this line right here, which passes through the point that we're given and through the closest point on the plane. We're going to find that line. So, well, the way we do it is if we need a line, we need two pieces of information. We need a point and we need a direction. Okay, well, let's talk about it. Do we know a point? Well, we know one point. We don't know the second point. If we knew that point, we'd be done. We wouldn't even have to start. So our point is 4, 4, negative 7. Okay, all right. How about the direction? Now is the time we say, hey, the direction is perpendicular to the plane, so it's the normal vector of the plane. So the direction, this is the normal of the plane, and therefore that would be, well, oh, be careful here, see? They have that z on sort of the wrong side. So let's rewrite this, x plus 2y minus 3z equals 5. That's how we would write it properly. Well, whatever that means. Come on, give me a break. All right. So our normal vector is the vector 1, 2, negative 3. All right. We've got our normal vector, we've got our point, and therefore, very easily we can write down our line. Okay, so we have x, y, z. We start by there. Put in the point, 4, 4, negative 7. Okay, and then the direction vector, plus 1 times t, plus 2 times t, plus negative 3 times t. Okay, so 4 plus t, 4 plus 2t, and negative 7 minus 3t. All right, good. We've made great progress. Now, what do we do? Well, what's our goal? We say, aha, next step. We need to find where does this intersect the plane. All right, so we know that this line goes through the point that we're interested in, and it also goes through the plane. So let's figure that out. And we say, okay, how do we figure that out? Well, what we do is we say, we have formulas for x, y, z, so we're going to take these pieces here, x equals y equals z equals, and we're going to put these in to our formula for our plane. So we get the following. X is 4 plus t, so we get 4 plus t, and now plus 2. Y is 4 plus 2t minus 3, and z is minus 7 minus 3t, and that equals 5. So again, this is x plus 2y minus 3z. So I'm just replacing the x, y, z parts by what they are in terms of the line. So let's clean this up. Now the good news, we're down to one equation, one unknown. Good. This is going to give us just what we need. So let's expand. 4 plus t plus 8 plus 4t and plus 21 plus 9t equals 5. Now, our t plus 4t plus 9t makes 14t. 4 plus 8 is 12. Add 21, 33. But we're going to move it to the other side. So it's going to become 5 subtract 33, which is also known as negative 28. Well, and now we say that tells us t is negative 2. All right, now, is that our answer? And why not? It's not our answer because it's not a point. What have we discovered? Well, what we've discovered is that at the time equals negative 2, in the current way that we're writing the line, that will give us the point which is nearest. Another way to essentially think about it is to say, really, we have our point, and then we have this direction vector, and it says, go 2 copies backward using the direction vector from your current point, and where you end up, that's the point that has the nearest on the plane. Okay, so we plug negative 2 into here, and we come to our conclusion that x would be 4 plus negative 2, 2, 4 plus 2 times negative 2, 0. Negative 7 minus 3 times negative 2, well, that's going to be negative 7 plus 6, which is negative 1. That's the point, and in fact it is the point. We found that point closest there. Now, before we leave this problem, I think that there's an important idea. We're going to do it again at least 1 or 2 more times in our various practice sessions. So let's go ahead and state it explicitly. We'll probably state it again later on, but I just want to state it explicitly now. That says, hey, if I have something about a plane, look for a line. And if I have something I'm trying to understand about a line, look for a plane. Now, why should that be the case? Well, if you think about it, is if I have a plane, this is really 2 dimensions, and so a line would be a 1-dimensional object. So when I have a 2-dimensional object, I have like one free direction that's perpendicular. So that makes sense to say, let me look for that on that line. Or vice versa. If I have a line, I can say, well, let me look at the plane that's perpendicular to that and find the right plane. So it's just a combination of saying, if I'm looking for something on the plane, is there an appropriate line that I can look at using the direction of the normal vector? If I have a line, can I look at some appropriate plane where the direction vector becomes the normal vector? And so there's this sort of mixture between these two pieces, the plane and the line. And if you say, well, I have a plane, let me see, is there a good line I could be using here? Or vice versa. And oftentimes the answer is yes. And if we understand that, it gives us power and an ability to solve more problems. And we should solve more problems. And speaking of more problems, here's another problem. What? What are the odds? All right. Find the point of intersection of the lines. So we have these 2 lines. X equals 3 plus t, 4 plus 3t for y, 1 plus 2t for z. But then there's this other line. Minus 2 plus 2s, 5 minus 2s, and 1 minus s. Okay, now it says that these lines are intersecting. Now in general, you have a couple of different things that can happen. You see, in dimension 2, if you have lines, there's 3 possibilities. One is they're right on top of each other, so they're the same line. Another is that they're parallel to each other, so they never intersect. And the other thing is that they cross. And so sometimes we say those are skew. So what happens in dimension 3? Well, you can still have the same line right on top of each other, parallel to each other, so that they never cross. You can have them cross at one point, or you can have them not be parallel, but that they don't cross at all. So it's a little bit more interesting up there. Now, it's said that these lines intersect. Okay, so we need to find the point of intersection. That's the part A. So how do we do it? Well, we have to find the point which is common to both. So we say to ourselves, okay, if it's the same point, the x values and the y values and the z values all have to be the same. So what we know is we have 3 plus t has to equal negative 2 plus 2s. 4 plus 3t has to equal 5 minus 2s. And 1 plus 2t has to equal 1 minus s. And now we have 3 equations and 2 unknowns. Now that should make you a little bit nervous, like, is this going to work? Because sometimes if you have more equations than unknowns, there's no solution. Well, we don't know yet. We're going to work through it. So what we're looking for is a way to solve. Well, the easiest thing to do is look for relationships and plug them in. Our last one, this looks so clean. Because notice, the 1's would cancel. And so we can come to the conclusion that the value of s is minus 2 times t. So there we go. That's a relationship. Now that you have a relationship, pick one of these 2 equations. Doesn't matter which one. Say we plug into the second one. Then we have 4 plus 3 times t is equal to 5 minus 2 times minus 2t. All right, well, that's really the same as 5 plus 4t. Now we move things around. And what do we get? Well, when we subtract the 3t from the 4t, we end up with t. Subtract 5 from the 4, we get negative 1. So it sounds like this should be at t equals negative 1. And then here, negative 1 times negative 2 says this should be at 2. So in other words, at different times, they're at the same point. But remember, don't get too caught up on this idea of time. This parameterization, yeah, sure, we have this extra parameter. We often think about it as time. But at the end, it's just like, here's a set of points. And so we have the set of points, and it just so happens that, for here, when we use the parameter, we get negative 1 is the right point. Here, we get 2. Now, technically speaking, we haven't actually finished part A yet. Because what's the thing we have to be careful about? At this point, we are confident that we have now said, look, if you just use the y and the z coordinate, those are the right values for s and t where they're going to match. So we are going to be guaranteed that y and z match. But we haven't actually shown that they intersect. It says find the point of intersection. So how do we know that they intersect? Well, the way we're going to know is we now say, okay, what happens here in this equation? Well, so we plug it in. And we can plug it into here, but better yet, let's just plug it in. So when we plug negative 1 in, we get the following. We're going to get 3 minus 1, which is 2, 4 minus 3, 1, and then 1 minus 2, negative 1. Okay, so there's our point. If we go by our first line. In our second line, what happens? Well, we plug in 2. Negative 2 plus 4 is 2. 5 minus 4, 1. 1 minus 2, negative 1. We say, aha, there's from the second line, and they agree, and therefore, that's our point. So, 2, 1, negative 1. Done. Done. All right. Now, on to part B. How do we do part B? Well, for part B, it says, find an equation for the plane containing the lines in part A. So what do we think? Well, we've got to find a plane. How do you find a plane? You need a point, and at this point, we actually have a whole slew of points, a smorgasbord, if you will, of points. And I might be saying, don't we just have one? And the answer is no. Any point at all on the lines can be used. And these lines have infinitely many points, so we're great for points. We do not lack for points at all. What do we lack for? The normal vector. Yes. See, the normal vector is going to be the place where we're going to put most of our energy into when we're looking for things like a plane. So, now we've got to start thinking, how do we go about finding the normal vector? And for that, if we don't have a clear path, we say, well, maybe let's not worry about the normal vector right away. Can we find things which are perpendicular to the normal vector? In particular, two different things which are perpendicular to the normal vector. Now in this case, we have two lines. And we go back to an idea we alluded to earlier. The direction of the lines are in the plane. In other words, we can put the vectors that are the direction vectors of the line, both of those lines will be in the plane. Both of those vectors will be in the plane. Okay, so we make an observation. The plane contains, and of course, we'll put that in quotation marks. What does it mean to contain a vector? Well, it means that by translation, we can put the vector so that both the start and end of the vector are in the plane. So the plane contains the vectors, and now we read off the direction vectors. 1, 3, 2. And here, 2 minus 2 minus 1. So now we say, oh great, our plane has both these vectors, so the normal has to be perpendicular to both. So normal is perpendicular to both. And now we're in our happy state. We found two things that we're perpendicular to, and therefore cross product. All right, good. Hopefully we're going to get really great at doing cross product by the time we've done all these problems. So we begin. I, j, k, 1, 3, 2, 2, minus 2, minus 1. I times 3 times minus 1, minus 3i. J times 2 times 2, plus 4j. K times 1 times minus 2, minus 2k. 2 times 3 times k, 6k. But subtract, minus 6k. Minus 2 times I is minus 4i. Subtracted becomes plus 4i. Minus 1 times j is minus j. Subtracted, plus j. So that would be 1, 5, negative 8. Let's check, right? Because our rule of thumb is we should check ourselves before we wreck ourselves. Because it's easy to make mistakes if we're not paying attention. So dot products, 3, 15, that gets us up to, 1. Got ahead of myself. 1 plus 15 minus 16, 0. 2 minus 10 plus 8, 0. So we're good. We're perfect, really. Fantastic. Now, we know that this is going to be perpendicular to these vectors, both of them. Well, the only vector that's perpendicular to two different vectors. See, when we're taking a cross product of two vectors in the plane, as long as the two vectors aren't parallel, when we take the cross product, the result is going to be a normal. That's the normal vector for our plane. So we're in great shape. We say we have our normal. Here we go. We'll call this n. N for normal. And now we say, look, our equation, these are the coefficients of x, y, z. So x times 1 plus 5y minus 8z equals something. All right, there's our answer. Other than we don't know the something. And here's where we use the point. So see, the normal, that's most of the work. The something, you need a point. So that comes down to the, hey, that something is like the translation, and you need to lock it in place. Once you know that value for the other side, you've locked your plane in place. So you pick a point. You could pick 2, 1, negative 1. Here's 3, 4, 1, negative 2, 5, 1. Any of them will work. So let's do 2, 1, negative 1. So we're going to put in x equals 2. So 2 plus 5 times 1 minus 8 times negative 1. And we'd have what? 2 plus 5 plus 8 gets us 15. All right. We claim that's the answer. Well, it should be, right? Because we did the work. Can we check it? Now, not every problem has an easy check, but if you can think of a check, it's not such a bad thing. Like when we did here with the cross product, we have a way to check. Well, let's pick another point that we know for sure is in the plane. 3, 4, 1. So if I put in x equals 3, y equals 4, and z equals 1, what happens? We'll get 3 plus 20, which is 23, subtract 8 is 15. Good. It should work out because it should be a point in the plane. Negative 2, 5, 1, minus 2. 5 times 5, 25. Okay, that gets us to 23. Subtract 8, 15. Good. Good. It works out. And it's nice to know that you did your job right. And we're going to get all the credit. All the credit. It's like Pokemon. We want to get them all. All the credit. Okay. Well, let's try another problem. So, a plane can be described as a set of the points of the form some initial point, x0, y0, z0, plus some multiple of a direction, plus some multiple of a different direction. Okay, and the multiples s and t are just any values you want. And you have these directions. are just two things that point in different directions. Now, it's not so surprising because what it says you start here and you move some amount in this way, then you move some amount in that way, and you get to everywhere you want to go. As a really super simple case, think of it in terms of the xy plane. You can say, look, the xy plane, you start from the origin and you move some amount in a direction we call x, you move some amount in a direction we call y, and now you're at a point. And that's how we get to any point in the xy plane. But now we say, look, there's nothing special about the xy plane. Just here's another plane. Here's a point. Move some distance in that direction. Move some distance in some other direction. And in all possible ways, you'll recover all possible points in your plane. So here we go. It says, write this plane, 0, negative 2, 3, plus s 1 minus 1, 2, plus t 3, 0, 1, in the more traditional form. All right, so we're in the sort of traditional equation form. In some sense, this goes back to what we were just talking about. One way you could think about this variation is similar to the vector format for a line. If you were to cover up, the end, that looks an awful lot like a line because it's a line. Okay, so what we're doing is it's like a line. It's a one-dimensional thing. And so then we're saying, aha, but now we can add this extra dimension coming in. Okay, all right, we're getting sidetracked. So a lot of this is just saying, do we understand what's happening? I think so. Then the next thing is to say, okay, we're looking for a plane. And we say, all right, well, if we need a plane, we have to say to ourselves, what is our point and what's our normal? Well, our point, we're told, is this part right here is the point. Because notice what it says, x0, y0, z0, doesn't explicitly say it's the point, but notice, set s equals 0, t equals 0, you end up with that expression. So this is a point. That's a point. And, it's a vector representing a point, is what we really should say. So 0, negative 2, 3. We could have chosen any value for s and t we wanted. We'd get a different value, a different point, but it'd still be a point in the plane by our convention. So if you have a choice, choose 0. 0 is a fantastic choice. And if you can't choose 0, choose 1. That's the general rule of thumb. Okay, so next thing, the normal. All right, well, how do we go about finding the normal? We know something. We have these two vectors here, 1, minus 1, 2, 3, 0, 1. They're non-parallel vectors in the plane. So we have two vectors in our plane. We're after the normal, which is perpendicular to all vectors in the plane. So we say to ourselves, aha, what we can do is the following. The normal, it has to be perpendicular to the vector 1, minus 1, 2, the first vector, and it has to be perpendicular to the second vector, 3, 0, 1. Now, once I have it's perpendicular to two different vectors, we say, well, there's something that crosses our mind, the cross product. So, we take I, j, k, 1, minus 1, 2, 3, 0, 1, and minus I, plus 6j, and plus 0k. All right, then minus 3k, but we're subtracting it. So plus 3k, 0i, but we're subtracting it. Well, 0i added or subtracted, it's still going to be 0. And then plus j, but we subtract, so minus j. So that looks like a minus 1, 5, 3. Well, let's check. Okay, so dot product. Minus 3, 0, plus 3. Good. Minus 1, minus 5, plus 6. Great. We did it. That vector is perpendicular to both the vectors we started, which is what our normal vector needs to be. So now we have our normal. Negative 1, 5, and 3. So point plus normal. Now we have everything we need to make our line. So our last thing to do is really write down the answer. Well, that's great. So what do we do? Well, these entries are going to be the coefficients of x, y, and z. So we get minus x plus 5y plus 3z equals something. And the only thing left to do is, what's the something? That's where the point comes in. We'll have minus 0 plus 5 times minus 2 plus 3 times 3. Well, minus 0 minus 10 plus 9 makes negative 1. And we're good. We're done. We're done. Fantastic. All right, that was nice. Really, this is kind of an interesting problem. It tests on sort of two things. Well, maybe really test on one thing. Do you understand how to read a definition and adapt to a slightly different presentation? But the other thing is sort of like, oh, you know, just like we can represent lines as starting somewhere and moving in a direction, we can represent planes as starting somewhere and moving independently in two different directions. So you might want to say, what about 3 space? And okay, now you're thinking. All right, good way to start thinking. All right, well, let's do one more problem. Here we go. Without using the distance formula. What? We love the distance formula. Okay, all right, fine. Whatever. Without using the distance formula, find an equation corresponding to the points x, y, z, which are equidistant, and equa means same or equal, and distant means distant. So same distance. All right, from 2 points, -2, 1, 4, and 6, 3, -2. And simplify as much as possible. Now, if you've been doing all the problems in our previous sessions, you might remember this one when we talked about distance. And you might remember there was a lot of algebra involved. We got a nice answer. So it's a repeat. But this time, there's no algebra. We're going to take the problem and think about geometry. So geometry is going to be sort of a stand-in for algebra. That's okay. In fact, it's more than okay. It's going to be beautiful. So let's think about our picture. So we start by saying, all right, we have 2 points, -2, 1, 4, and 6, 3, -2. This is the hardest part to think about, is what would be the set of points which are equal distance from both. Once we can agree on that, the rest of the problem will be beautiful. Well, the answer is it would be a plane. Now, if you're not comfortable with that, think about it this way. Suppose you had not these 2 points which are sort of somewhere in space like this, but suppose they were directly on top of each other. And let's say this one was at 0, 0, 1. This one were at 0, 0, -1. What would be the set of points which are equal distance from both? Well, it'd be the xy plane. The thing is, it's the same scenario. We've just turned space and scaled. And so if you think about what's happening, it's no matter which point you go down here, it reflects, and it's the same down there. So in other words, the distance from this point to there, by symmetry, is the same as the distance from that point to down there. So there's sort of, essentially what you have is the mirror is the plane. It reflects. So it's like, okay, whatever this line segment is, it's going to be the same down below. All right. That's the hard part. That's the, can you see that geometrically? Now, if you can't, well, we always got algebra as a stand-up. As a backup plan. But let's suppose we see it. Okay, from here, we're going to be saying, okay, so it's a plane. Great. But how do we find the plane? Well, since it's a plane, we say to ourselves we need 2 pieces of information. what are our two pieces of information? We need to find a point and a normal vector. I find myself, I don't know why, I keep drawing that I as if it's a lowercase I. I don't know. It's strange. I got to get out of the habit. So let's think if we can find something. So right now we don't have either of those things, but what is an easy point which is guaranteed to be on the plane? In other words, is there an easy point to find which has to be the same distance between our two original points? If you will, it would be a sort of a halfway point or a midpoint. Yeah, the midpoint will do it. Okay, so it's like, cool. So for our point, we're going to use our midpoint. All right, so how do you find the midpoint? Well, what does that mean? Well, what the midpoint would be represented by is if you took this line segment connecting these 2 points and said, let's find the point halfway there, right in the center. The way you find the midpoint is you take each coordinate and you average the two values. So you add them together and divide by 2. 6 plus -2 is 4. Divided by 2 would be 2. 3 plus 1 divided by 2 is also 2. 4 plus -2 divided by 2 is 1. So 2, 2, 1. So again, you take each coordinate and add them up, and then you divide by 2. So that's how you find the midpoint. So now we say, fantastic. We have 1 point. 1 point that's definitely on the plane. What else do we need? Well, we need a vector, the normal vector. Okay, so how do we find the normal vector? Well, we need to start thinking about the geometry. So our geometry says if we need the normal vector, we need to find something which is perpendicular to our plane. So we start looking at this and saying, do we have anything which is perpendicular to our plane? And we do. Look at our picture. This is perpendicular to our plane. So the line segment that directly connects the 2 points is perpendicular. We say, perfect. Look, now that we have this, all we have to do is find some vector that's on this line segment. So pick 2 points and connect them with a vector. Doesn't matter which 2 points, so you have lots of choices. You could pick the 2 original points, or you can choose the halfway point. Doesn't matter. It'll still be a vector. So let's suppose, well, let's pick from the point -2, 1, 4, and let's just go to the midpoint. -2 to 2. Our change would be 4. Went up by 4. 1 to 2. -1 went down by 1. 4 to 1 went down by 3. Okay, so there we go. That's the vector that represents from our original point to our midpoint. And by the way, it's the same vector that, whoops, this -1 is wrong, right? Because I went -2 to 2 was up by 4, 1 to 2 is up by 1. Aha. See, what I was going to say, and I forgot my comma, whatever the vector that went from here to the midpoint is the same as the vector from the midpoint to there. It wasn't working, but now it works. See, 2 to 6 is 4, 2 to 3 plus 1, 1 to -2, -3. There we have it, our point and our normal vector. Put it all together, and what do you get? Well, we get the following. This is our coefficients, so 4x plus y minus 3z equals something. Now, only thing left to do, what's the something? So here's where we use our point. So 4 times 2, 8, plus 2 minus 3. 8 plus 2 minus 3 is 7. And there we go. 4x plus y minus 3z equals 7. That's our plane. That's the equidistance between the 2 points. And if you go back and compare, this is much, much faster than what we did before. We could save ourselves a lot of work, but it relies on our geometrical intuition. So geometrical intuition can save a lot of work. And the nice thing is, it really helps us understand more about what's going on. Sometimes the algebra hides beautiful ideas. And not that I'm ever going to say anything bad about algebra. It's a fantastic thing. But I want to say good things about geometry. It's great to be able to understand what's happening. And to do that, you got to keep practicing. So we did a lot of practice now. There's a little bit more practice coming in another session. So keep it up, and you'll be doing great.